Welcome everyone for our latest series. What is it, series 4, Professor Wagner, that we're
Been a
doing?
while.
Yes.
Been quite a few.
So thank you for joining us on this episode 1 for this evening's presentation with Professor Mitch Wagener of the Western Connecticut State University Department of Biology. And again, this series will focus primarily on climate change and other related topics. So without further ado, Professor Wagner, you have the con, sir.
Thank you. This is my trusty sidekick Ringo, the the terrier mix. Hopefully he won't be a pill. All right. So I always start with my science building picture. I also have a winter one that I just took this last week, and next time I'll try to remember to put that there as a contrast of sorts. Okay. Let's see what this is about. This is a talk that I put together to participate in the program that another library was doing on that with the cooperation of NASA. And this was about the problems of potentially colonizing an exoplanet. And we'll define what an exoplanet is and why it is something that may take a while before we actually attempt, if we ever do, and so on. So when I mean transplanting human civilization, or if I talk about moving the planets, what I mean is how do we reestablish a human civilization in a new location that's likely to be very different than what we have now. Well, an exoplanet is a planet that is observed, and these are real and have been found orbiting around other stars. There's a variety of ways which they are detected, including a periodic dimming as the planets orbit those stars, and a number of other things that are way too physicsy for me to understand entirely, but it's all very interesting. And I would expect that stars, there's zillions of them in our galaxy alone, such stars would have a good chance of having planets orbit them like our star does. And the chances are that there are some stars that are some planets around stars of the appropriate size and temperature and all that jazz that would potentially support human life. It's speculation because we haven't been there yet, but just you've got to think the chances are that is probably true. After all, we could probably build colonies on Mars should we desire to do so, although it would be rough going for a while. But anyway, that's a different story. As of the 10th of May 2024, there have been 5,626 exoplanets discovered, all from things we observe from Earth, in 4,183 planetary systems, including 949 multiple planetary systems, a star that has more than one planet. Several thousand additional exoplanets are not yet confirmed. We suspect that they are there, but have not yet confirmed. And that's quite a few, actually, considering how hard they are to detect. This is a artist rendition showing the variety of the ones that have been discovered so far. Some of them look very much like planets that we have in our solar system, even though some of them are hugely larger. and some of them are fairly small, and some have rings, and some of the gas giants, and some are stony planets, and all that as best we can tell from here. And we have to do that through looking at the nature of the light that's coming from them and so on, or bouncing off of them. But what they are like on the surface, we don't know. Now, for a exoplanet to be appropriate for human settlement, if we ever find any that are, they would have to be in something we call the habitable zone, which is that zone where that's the right distance from the star. And that would vary how far that would be, depending on how bright the star is. In the right zone around the star for liquid water to exist. It's a Goldilocks zone, not too cold and not too hot. Okay. And the study of planetary habitability also considers a wide range of other factors determining the suitability of the planet for hosting life. For instance, what kind of planet it is. If, you know, if it's a binary star system and all where there's two stars and planets are orbiting and all that stuff. Here are a selection of some that have been discovered. Notice that all of them are larger than Earth. That is a function, no doubt, of the fact that they're so far away. That maybe some of the ones that are Earth size and smaller, just we haven't detected them yet because they're small. And some of them are relatively nearby. Tau Ceti E is one of the more close ones, although that star is still light years away. And we'll talk about light years here in a minute. So there's a variety of them, and we know a little bit about these planets, but not a lot. Now, first of all, a little bit of astrophysics. Stars generate power, generate energy through a process called fusion. It's a nuclear reaction where small particles, neutrons and helium atoms, neutrons and protons will be jammed together by a strong force of gravity, and they will fuse together to form helium. And as they do that, they generate lots of energy. That's how our star generates its power. It's also the way that fusion bombs are how they generate their massive power. Okay, fission is a different thing. The Hiroshima and Nagasaki bombs at the end of World War II were fission bombs, where a large molecule of uranium in one case and plutonium in the other is split apart. And in splitting apart, they release energy, but they release less, if you can imagine that, than a fusion bomb would. Anyway, so this is the way stars produce their light. Now, our star is no different than the others in this regard. At some point in the early solar system, enough of this hydrogen came together in its various isotopic forms, deuterium and tritium. Deuterium is just a hydrogen ion with a hydrogen atom with an extra neutron stuck to it, and tritium is two extra neutrons, so it's heavier versions of it. Anyway, when enough of this stuff was pulled together by their joint gravity, which would take a while for that to occur, then they reach a critical mass and they ignite, and then let there be light. Okay. And obviously it's not a particularly rare event considering how many stars there are in the sky. even just the ones that you and I can see. And there's gobs more out there that we can't see. And they all have their own particular characteristics based on what other elements are found in there, whether there's certain amounts of iron and other kinds of elements. And these are things that can be studied from Earth too. And we get some idea of the nature of stars in terms not only their stars, but how bright they are and what other kind of elements other than hydrogen are inside of them by examining the light. Well, in addition to the star, there were flakes of matter that were bopping around as well. And as the star coalesced and ignited, it had a great deal of mass, and therefore it exerted gravity on these little bits. And the little bits would stick together by hydrostatic processes and making somewhat larger bits, which would then come together eventually via gravity, making rocks, and eventually they would form into planetoids and planets. Now, some wit once said that if you had a teacup the size of Jupiter, it would, on its own gravity, collapse down to a sphere because of the mass of the object. And that's why everything above a certain size and mass out there in space is spherical or close to it. There are reasons why sometimes they're a little bit out of round, and I'll talk about why Earth is in a minute. And so that's how our planets and asteroid belts and things like that came about. The asteroid belt between Mars and Jupiter is not a planet that broke up, but more likely one that just never quite came together because of the gravity of Jupiter on one side and the sun on the other. It kept pulling things apart. Well, the early Earth was a bunch of hot rocks. And it took a while to cool down to a point where gases where water, which existed here, could become liquid water. And so it was a big hot rock. In fact, you can dig a hole in your backyard trying to dig to the other side of the earth. You'd never make it, of course, but if you dug down far enough, it'll get warmer and warmer and warmer. And you could potentially get down into the middle of the earth where it's really hot, and that heat is left over from this very thing, this residual heat from the formation of the solar system. All right. Now, this early Earth, while it was still young, collided with an object about the size that Mars is now. Okay. Astronomers call this object Theia. I think it's probably related to the names are related to the Greek myth of Athena coming out of the headache of Zeus. In this case, it was Theia slamming into the Earth, which changed a lot of things and is one of the reasons why the Earth is hospitable to life to this day. The Theia got consumed within the Earth, but the force of the collision knocked two chunks of Earth out into space, which stayed within the orbit of the Earth and gradually came together and formed what we know as the moon. But and there she is. And we know this now because we've been to the moon. We've collected rocks, we brought them back, we analyzed them and found out that they had the same geological chemical signature as Earth does, which we wouldn't expect from something that had formed separately and got captured by the Earth. Well, the early Earth contained all sorts of things, including gases and water and dust and all that sort of stuff. And or the early Earth outgassed. That's how the atmosphere was formed. And things that were the lightest, like helium, came out first and basically kept on going. Our atmosphere does not contain much helium because helium is so light, it is acted upon less strongly by the Earth's gravity. Volcanoes to this day releasing gases from the hot part of the Earth and in a form what's called outgassing. A lot of it's CO2. Well, as the early Earth cooled, water that was in the gaseous form at the poles began to condense and form lakes and oceans and so on. One of the reasons why we don't see a lot of craters on the surface of the Earth is that we have a hydrologic cycle. We have rain and things like that, which erode them away. There are a few, but they are relatively recent craters. Or some suspected craters like Hudson Bay in Canada and things like that. Because anything that marks the surface of the Earth gets eroded away over time. And when water became present on Earth and cooled down to a certain point is the time that Earth or that life probably formed. The mechanism by which it formed is not well known. There are theories, there are suppositions. It's one of those things that we may never know for sure. But the first life was, of necessity, something very similar to bacteria, because there are lots of bacteria that can live without oxygen, and there was no free oxygen in the atmosphere. But that those bacteria and the DNA that they use for reproduction and inheritance is our DNA as well, and it is part of the great chain of terrestrial life that we study in biology. And what unites us all is this stuff called deoxyribonucleic acid, which is DNA. Now, ecologists talk about that portion of the Earth on, in, and above the Earth's surface where life exists, and we call it the biosphere. Okay? Because there are parts of the Earth down deep where are probably too hot for rocks to, for life to live, although there's life probably much deeper than we had previously thought. The biosphere is a closed system. We're not importing things from outside with the exception of solar radiation and cosmic radiation, and heat from the interior of the Earth. That being said, it's largely self-regulating, with the unfortunate aid of some human activities which have thrown the balance off a bit, but that's for a different topic. And on that surface of the Earth includes that portion of the Earth which is covered with the gases, and that's the atmosphere, which you can see from those Apollo photographs. That's where the clouds are. You can also see the hydrosphere, which is where the water is, and our weather and our climate systems are based on movement of air driven by heat and density of the air through the seasons, and driven by the spin of the Earth, called the Coriolis effect, which causes the air in motion to appear to be deflected by an observer on the surface. I could go on and on about this stuff. This early atmosphere, as best we know, we cannot tell what the content of the atmosphere was much before 4.4 billion years ago because it did not leave many clues. We can only suppose. But starting with 4.4 billion years ago, we have some clues in rocks. And like now, the atmosphere was mostly nitrogen. There was quite a lot of carbon dioxide. There was quite a lot of water vapor. It was still too hot for much of it to have condensed out. And there was also methane and ammonia. No oxygen. Oxygen is a element that reacts strongly with rocks and things like that, and so it holds on to those rocks until life existed that would turn it loose. Life is required, at least under the conditions we have on Earth, for there to be oxygen in the atmosphere. As the world Earth cooled, then the amount of water vapor in the atmosphere went down because it condensed out as oceans and so on. And so the hydrosphere is that part of the earth covered with water. And the lithosphere are the rocks, which are more active than one might think, because it's still hot down there and underneath the the crust of the earth. And hot rocks, as sufficiently hot, are semi-liquid and tend to move around as convection currents like water and air do, only much more slowly. And that's the reason why the continents move around and why we have volcanoes and earthquakes and all that stuff. Now, inside, one very important thing for the presence of life on Earth, which is something I'm bringing up because it's something that we would require in a home in an exoplanet, is that the core of the Earth is about the consistency. It's still very hot, and it's about the consistency of peanut butter, and it spins. It spins like the Earth itself spins, but it spins at a different speed than the outside. The inside core, which is metallic, spins at a different speed than the outside core, the outside surface does, and that makes the Earth a huge magnetic field generator. Okay, and that's a good thing. That's one of the things that allows us big critters to survive, because there's lots of radiation being released by the sun, which would be very harmful to living tissue if it could reach the surface. And that is minimized by the fact that the Earth has this mechanism for generating a magnetic sphere, which we see as the north magnetic pole and the south magnetic pole in your handheld magnetic compasses and all that stuff. And that field around the Earth deflects much of the most harmful radiation, including the particles being released by the sun, and so on. There's also the cryosphere, which is ice. And ice is active, and it's in interaction with the water, because of course it's frozen water and so on. But that is another talk that I will be giving at some point, is talking about the importance of ice and permafrost, but not this one. Now, one of the reasons we have had over Earth's history, through Earth's history, we have had a number of really cold times and really warm times. And these are caused, the ice ages and so on. And they are caused by something called the Milankovitch cycles. And they all relate to, well, two of the three of them relate to that collision of Earth with Theia early in Earth's history. Earth slamming into this object made the Earth knocked it on a tilt so that instead of the axis of rotation being 90 degrees from the sun, we are 21 degrees off kilter. That allows Earth, as it rotates, to have changes in seasons, increasing the variety of habitats and the diversity of life. Okay, I say these because these are things that we would probably look for if we were looking for an exoplanet to colonize. Another thing is that with that collision, there were irregularities in the density there, so the Earth is lumpy on the inside, and so it has a wobble to it, and that's called it's the eccentricity. It's of the spin, and so it kind of wobbles like this over long periods of time. In Boy Scouts, you probably, and maybe Girl Scouts too, learned that you could tell north in the night on a clear night by finding the North Star and tracing it down to the horizon, and that's roughly north. Well, that's true, but the wobble of the Earth means that that Polaris is not always going to be our North Star. It will be something else in a few tens of thousands of years because the world is wobbling. All right, and because of the orbital tug of the Earth from Jupiter and Saturn and the Sun, the Earth's orbit around the Sun is not circular, but elliptical. And that shape of the ellipse changes over time. Okay, so you have these three things. You have an irregularity in the shape of the orbit of the Earth, and some parts, some phases of that are warmer for the Earth and some are cooler. You have a variety changes in the axial tilt, some of which are warmer and some of which are cooler, and likewise with the wobble. If you have all of the warm things pop up at the same time, then Earth moves into a warm phase. If you have all the cooling phase happen at the same time, you go into an ice age. Okay, and so that's what causes ice ages to form, and the interglacials between the ice ages to come out, can't come up too. And those things take tens of thousands of years to happen. All right, so the collision of Theia into Earth and it was very important for making these things, two of these three things happen. And so thank you, Theia. The orbit, the axial tilt varies between 22.1 and 24.5 degrees. You can look it up and find out exactly what the orbit axial tilt relative to the sun is if you're interested. Now, another thing to consider is the nearest star is Proxima Centauri, I believe, which is between 3 and 4 light years away, which means that a photon of light, one particle of light moving at the speed at which light moves, would take 3 to 4 years to move from Earth to that sun, from our sun to that sun. Okay, and we don't know whether that particular system has appropriate planets or not. Okay, so what I'm saying is that's the nearest thing we have. So in order for that a ship from Earth to make it to Proxima Centauri, it would have to be really, really fast if you are going to be able to make the trip there within the lifetime of one set of astronauts. Okay. The other option is to have multi-generation ships that can keep generation after generation of humans alive for the long trip it would take to get to wherever you're going. Okay. Most of those candidates for colonization would be much farther away than Proxima Centauri, or go into some sort of deep sleep so that you go into suspended animation, or you develop a ship that's much faster than we can currently build. Okay. One of the things that Einstein discovered is something called relativity. And relativity tells us that as if you take an object and the closer it gets in speed to the speed of light, which as far as we know is the upper limit to how fast anything can go, the slower would the time pass for a rider on that object. So you can have a rocket, you can have twins. One of them gets on a rocket and goes to Alpha Centauri and back at 99% of the speed of light. By the time the traveling twin went there and came back again, the twin that didn't move would probably have died of old age, while the time as perceived by that individual in the rocket would have been very little. It would not have, he or she would not have perceived much time elapse at all. Okay. So it's something called time dilation, and it's a little hard to wrap your brain around, but that's relativity. All right, now let's say that we figured out a way to get there. Well, we'd have to think about our civilization. How would we order ourselves on a new planet, given that we could start from scratch? Okay. There would be difficulties of starting fresh. Okay. For one, help's a long way off, and there's no way to ask for help that is not something that would require a very long time to get here. Okay, so you're on your own if you colonize an exoplanet. We won't know much about that planet before we land. There may be human pathogens that mutate extra fast in the conditions of the planet and cause problems. We don't know. There would be huge decisions that would have to be made by the colonists. Should you try to change that planet into a form that is more Earth-like, or leave it in its native state and just kind of make do? These are not insignificant questions, and there's lots of implications in the way you might do these things. There are advantages of starting from scratch. You wouldn't have competition with other organisms of our size that you know of, but who knows, right? We can build the civilization that we want. What do we want? Can we really? Are we genetically hardwired into a particular set of reactions relative to each other that would keep us from getting very far away from what we did on Earth? I don't think anyone can answer that question. There's human interactions. The first colonists will be mostly scientists and engineers. It'll be a relatively small set of sample of Earth type of people. And they will, you don't really, how everyone's going to interact long term. They'll have to focus on surviving, then building and making. And they will be the product, will out of necessity be the products of many nations and many cultures, each of which has its own baggage. We take ourselves with us when we go that far away, and we go to a place that we cannot reasonably return. Survival on an exoplanet will require change. Change in how do we take responsibility for our actions? How do we make decisions? How do we prioritize? How do we see the world? Albert Camus, French novelist and philosopher, wrote a novel called The Plague, where the main character is dealing with a plague in Algeria and pondering what it told him about the nature of humanity. And the character says, I have to tell you this, the whole thing is not about heroism dealing with this plague. It's about decency. It may seem like a ridiculous idea, but the only way to fight the plague is with decency. I have long said that the best way to deal with climate change is with human decency. And all these people, all these brainiacs, geniuses who are the people with the skill sets that would be sent to the exoplanet, if that were to happen, would have to deal with each other with human decency, and that might not be easy. And we have to remember that what in our new home, as in our old home, what is best for our grandchildren will be what's best for us as individuals here now. And any effort to build a new society must be built on the greatest ethical concept, which is the golden rule. Treat other people the way you wish to be treated. How is there any other option? In a brave new world, the golden rule must apply to people on the other side of the world who we have never met and to the future generations not yet born. That is also true of the way we need to deal with our fellow residents of planet Earth now. As Carl Sagan told Congress, we all live in the same greenhouse. If you're interested in these scenarios, there is a series of novels by my personal favorite science fiction author, Kim Stanley Robinson, called Mars Theory, Mars Series, Red Mars, Green Mars, Blue Mars, about the human colonization and terraforming of Mars. And it covers some of these interactions that we're talking about. Now, think about going to one of these planets that we know very little about. Robinson wrote another novel about a multi-generation ship going to colonize the next planet. Okay, and the name of that book is Aurora. Also quite good. But this brings the following question that I want to leave with you. If we are capable of finding and reaching an exoplanet that can support us, if we're smart enough to survive in a new and very different place, if we are emotionally and intellectually capable of building a brave new world from a small group of initial settlers, then why can't we fix the beautiful world that we have now? And that's my link to climate change for this talk. If we can do all that, then we can fix what we've got. Okay, that is the end. I'd be glad to answer questions if there are any questions that you might have.
We have a question from Bill S. Is there another compound like water that is liquid at a different temperature that might support life as we don't know it?
Possibly. It would be life built on a very different chemistry than ours. You know, our life is water and carbon. Carbon has a particular chemistry that if you took organic chemistry or in biochem, you would have studied it, a particular kind of chemistry that reacts in certain ways within the temperatures and pressure and the conditions we have on Earth. Therefore, it became the foundation of life. Silicon there's been speculation of silicon also being a molecule that could form the basis of life under different conditions. So maybe it's a very interesting thing to consider.
Do we have any other questions? Please type it in the chat. I will relay it to Professor Wagener. Also, if those books that Professor Wagener by Kim Stanley Robinson. If you're interested in those, I'm sure we can, if we don't have them in our collection here at the Danbury Library, you may be able to request them and we can get them from different libraries across the state.
He wrote a lot of other books too, and all of them are worth considering. Some of them are brilliant. One is called the Ministry of the Future, about human institutions that are able to deal with climate change.
Awesome. Yeah,
Yeah.
if we don't have it here in our collection, please feel free to request it from one of our librarians here through interlibrary loan. We have another question from Francis. How would we construct structures on new planets that we would decide to colonize?
Well, we would have to probably use the metals that we found there on the planet and build factories that would, you know, produce the aluminum and iron and things like that we would need. We probably would be able to tell some things about the planet, whether there was a signature of aluminum and iron and other things, magnesium, from here, or at least have a reasonably good guess that stuff existed. But, there's always a possibility that maybe there wasn't as much as we thought, and we'd have to come up with new things. It's not impossible for this to work. It's just harder than anything that we could do to fix things here, which is the point I'd like to make.
Another question from Bill. What size of population would be required to survive on a new planet?
That's a good question too, because there's a certain level of genetic diversity one would need for the health of the human population. So you couldn't send 5 people or 6 people out to a place and expect them to form a healthy population, even if they got along. And who knows whether they would. You know how people are. And they may all kill each other before they even got there. But you would have to have hundreds of people, I would think, just to have a genetically viable population that wouldn't have birth defects and genetic diseases and things like that become more common. Plus, you'd be exposed to a certain amount of radiation on the trip. You couldn't avoid that, and so who knows what kind of genetic mutations you'd find along the way.
Yeah, there are a few science fiction movies that actually take those things that you've spoken about into account. Total Recall with Arnold Schwarzenegger. The first 2 prequels of the Alien series, Prometheus and Alien Covenant, take a lot of that into account. And another question from Bill, and another good question from Bill. What if the new planet was already populated?
Well, there you go. You have to question, would then their population be one that we could or would recognize? Could or would we learn to communicate with an organism that evolved in a very different place under very different conditions and very different time? Would we even be able to relate to them? Would we even know that they existed? This is the fodder of unlimited amounts of science fiction novels and movies, potentially.
Yeah, that's a very good question, and that's something that we still don't know until we get there. That's sort of that would be like going back to some episodes of the original Star Trek series and seeing how you deal with
Yeah.
that sort of circumstances.
If faster than light travel were invented, warp drives or whatever the hell, that changes everything. But we currently don't think the physics allows such things, as my understanding. I'm not a physicist, I'm a biologist, but
And that remains to be seen until
yeah,
the
yeah.
physics, gets seen in a different vantage point, or or understanding of how everything is, has another sort of like theory of relativity moment by like a person like Einstein, where we see things completely differently.
Mm.
I think we're overdue for something like that. A couple of questions from Alex to you, Professor Wagner. When was the first exoplanet confirmed?
I don't know. I think it was, I'm not sure. I have to say I don't know. Probably in the last 20 or 30 years, but I can't say that for sure.
Mm,
And it would have been something on maybe one of the Tau Ceti planets or something that's reasonably close. It's a tricky thing detecting these things, and astronomers have figured out new ways to do it. Um, and so, one can find out that information. I just don't have it in my brain.
that would be something you can look up on Google.
Mhm. Yeah,
Or
probably
come
could.
into the Danbury Library and ask one of our reference librarians. I am not a librarian, I'm just a lowly technology program coordinator. So I'm sure that question can be answered for you. Question from Francis. How would those that have decided to colonize the new planet supply themselves with a substantial food source?
Well, that's a good question too. There are microbes you could colonize to make food, which is probably fairly nutritious. Would it be tasty? Would you want to jump after a year of eating the same slop? Would you want to jump out of the porthole of the airlock of the spaceship? Um, that is, you would probably have some pretty damn good cooks to take stuff that is grown on the ship and cook it
Exactly.
such a
I think
way that everyone would go nuts.
they would have to have some sort of like vertical or tower garden
Yeah, yeah, there you
infrastructure.
go.
And
Yeah.
by the way, we have a tower garden here at the Danbury Library. Feel free to come by and check it out. It's on the main floor. Do we have any other questions before we sign off for this evening? I know it's um, a nice cold night. Oh, here we go. I would say yes for Bill S. Um, was the movie The Martian realistic? I think I can answer that. I think it's almost 100% yes, except for one scene. And you need to back me up on this.
I haven't seen the movie, so I don't.
Really?
I haven't seen it.
Okay. So I did a little bit of research on this myself, and pretty much the entire movie, The Martian, is realistic except for one scene. The scene where they have the what is it, the dust storm, the wind that comes out and everything, like that has to, that knocks them out. They think that Matt Damon's character is left for dead, and they do the escape from Mars back to Earth, the rest of the colonists, the rest of the scientists and everything. That is not true, because of the gravity on Mars is lesser than on Earth. um the wind wouldn't be that strong.
Yeah, the
So it wouldn't be
air,
that
the air
strong.
is much thinner, less dense. That
Yeah.
that is true. And so they have
So
lots of wind, but it's pretty weak wind.
it would be like the most forceful wind you would get there would be like a cool breeze, so to speak. It's not going to be like a hurricane type sort of like wind or anything like that that will knock people down. It will be far from that because of the gravity. So there you go. But the rest of the movie is pretty darn realistic. So that for being said, you have anything else to relay to us all, Professor Wagner?
No, I think I've gone off on a limb about as far as I can go.
Okay, excellent. Until next time, please, folks, feel free to register for our upcoming presentation, episode 2 on the 6th of February. And until then, I bid you adieu and have a great night.